Hey guys, we're going to be looking at optimization, mainly with maximum area and finding maximum volume. Okay, before we get started, there are some steps that you need to do before you can find out maximum area and maximum volume. I guess I'll go through the steps first, and then I'll give you an example of a question, and then we'll go from there, all right? So there are some key ideas. So with these key ideas, the first one is identify the quantity to be maximized or minimized. So in majority of calculus problems, you'll be working with things like volume or surface area, just to get you started. All right, the second point is write an expression for this quantity, and the expression should only have one variable. All right, this is really important because when you want to differentiate this function, you have to have just one variable. Again, it'll make sense when I go through the example. The third point is differentiate this expression. The fourth point, equate this expression to 0. And once you do that, solve the equation that is f dash of x is equal to 0. So the next part, you need to substitute the solution into the original equation. And once you do that, the last part is using the second derivative test to figure out whether the point is a maximum or a minimum. So these kind of 7 key points, if you kind of remember them and you kind of work through them, you should generally be able to optimize maximum area, maximum volume, and problems like that. All right, let's have a look at an example. So in this question, a fairground operator wishes to build a marquee in the shape of a cuboid on a square base with 2 opposite faces open. She has 1,000 meters squared of canvas available and wants the maximum possible volume of the Okay, so before you start, like with any calculus problem, it's always good to just draw a rough diagram. So in this case, this is what the shape of the marquee is going to be, where it's got a square base and the top is going to be a square. So let's just label some of these sides. If that's x, that's also going to be x because it's a square. And we have height there. So just filling in the rest of those measurements. As you can see, you've got x and then you have h. Now, we also know that she has 1,000 meters squared of canvas available. So what we can do is we can make a net of this particular shape. And the net should look like this. Alright, so that's the left side right there. That's the top and the right side. Now here you have your left side, top, and right side. So now we just need to match up the measurements. So we got h, we got x, we got h there. That's x. So the only thing that remained is, so imagine this pink outline. This is the amount of canvas that she has available. So the area of this pink rectangle is going to be 1,000 meters squared. Okay, now that we have all this information, we'll actually go to step 1 and work through from step 1 to step 7. So I've just drawn up the 2 shapes right next to each other just for a quick reference. Alright, so the first point, bullet point was identify the quantity to be maximized or minimized. So in this case, we know that we wanted to work out volume. So volume of a cuboid is equal to length times width times height. And in this case, the length is going to be, well, I mean, it doesn't matter which way you do it. You're going to end up with x times h, or x squared h. Alright, looking at the second bullet point, or the second point, it was write an expression for this quantity. The expression should only have one variable. So if you remember at the top, we have volume of x is x squared h. Now, we have x and h. We need to get rid of h. And I guess the best way to go about it is use that second bit of information that we have. Because we know on these that the cross-section, or sorry, not the cross-section, the net of this canvas, it should be 1,000 meters squared. So we know that 1,000 meters squared is the canvas. So what we have is, we have that area, sorry, I'm just going to write this available. So we know that the length times width is equal to 1,000 meters squared. Now the length, which could be base, could be 2h plus sorry about that, press the wrong button there again. We got 2h plus x multiplied by the width. In this case it's going to be x, and that's equal to 1000. So what we can do at this point is we can rearrange things so that h is by itself, or write h in terms of x. So what I'm going to do is I'm going to expand it out. 2hx plus x squared is 1000. Rearranging it, 1000 minus x squared. So h is equal to 1000 minus x squared divided by 2x. Now you can simplify further if you want to, guys. I mean, it doesn't really matter. At the end of the day, you're still going to end up with the same answer. Alright, so now that I have h in terms of x, what I could do is I could replace it in the volume function. So volume of x would then equal x squared times h. But h is actually equal to 1000 minus x squared divided by 2x. Which, when you simplify it, would equal 500x minus x cubed divided by 2. Okay, from this point we're going to go on to our third point, and that was to differentiate this expression. So we had volume of x is equal to 500x minus x cubed divided by 2. So differentiating this, we're going to get 500 minus 3x squared divided by 2. So once we differentiate this expression, we want to go to the next part, which is put it equal to 0 and solve it. So there we go. Equate the expression to 0. So 500 minus 3x squared divided by 2 equals 0. And now we need to solve this for x. So solve the equation that is f dash of x is equal to 0, or in other words, you put the gradient equal to 0 and solve it. So we have 500 minus 3x squared divided by 2 equals 0. Rearranging everything, we should get x squared is equal to negative 1000 divided by negative 3, or x squared is equal to 1000 divided by 3. So therefore x is equal to square root of 333.3. Now simplifying this, we're going to get x is equal to 18.26 meters. Alright, I know that square root of a number would give me a positive value and a negative value. In this case, you can't have a negative 18.26, therefore we're going to ignore it, and we're just going to choose to work with the positive value, which is 18.26. Okay, so once we have this value, we go on to step 6, which was to substitute the solution into the original equation. So we have volume of x, so this was the original equation. Notice I've actually kept it with x, so that I don't have to go find what h is and then do this whole thing again. So volume at 18.26 meters, it's just a matter of substituting and solving it. So doing this very quickly, you will end up with 6085.81 meter cubed. Okay, and the final step is to figure out whether it's a maximum or a minimum, and of course prove that it's a maximum, because that's what this question was originally asking us. So v dash of x excuse me, equals 500 minus 3x squared over 2. So v double dash of x would equal negative 3x. So now it's just a matter of substituting 18.26 in v double dash, and we get a value of negative 3 times 18.26, which equals negative 54.77. And because this is a negative, therefore the point has to be a maximum. That means this has to be a maximum volume. So guys, this is pretty much, how do I say it? It's almost like a bread and butter question. You know, you just got these 7 steps that you got to follow for optimization, and just follow them, and you know, it's just bringing them all down to one variable first, then you got to differentiate it, put it equal to 0, and find out what the value is. Alright, that's all I've got for the session. Apologies about a long video, but thank you for watching anyway.